Hello, and welcome to our final live stream for 2018. Today I'm going to be talking about testing and instrumentation for fresh concrete, but a few housekeeping issues first. If you haven't joined us before, this is a YouTube live stream, so on the right-hand side of your screen, you should be able to see a live chat window. And if you have any questions or information you'd like, I'd be very happy to read them there and reply. Other than that, welcome. Now, a little bit of news to begin with. We are proud to have launched a new unit within our company, a separate business called PCTE Industrial. Now, PCTE Industrial is going to be the home to a variety of industrial non-destructive test equipment, including metal hardness testing, ultrasound equipment, and more. This is an exciting new business unit. Our manager for this is Warren over in WA, and he's level 3 technician in a number of different non-destructive tests unique to metal and industrial NDT. As a beginning to the range, we've launched the ProSec Equitip as something we can supply, which is the unit pictured. We also have UT kits and have just come back from an international conference and should have a lot more to announce very soon. Also from ProSec, we are very, very excited to announce some new firmware updates for our popular ProSec GPR Live system, which has introduced alternate reality or augmented reality, and we are now able to physically overlay the outcomes of our radar scans on the ground when presenting to clients. This also is one in a long string of upgrades the ProSec GPR has had this year, including the power cable detection functionality and infinite stretch and compact on the view and more. If you'd like to learn a little bit more about what the ProSec GPR can do, please let me know. And we also have demonstration units moving around the country regularly. Continuing with ProSec, the Pundit Live Array systems have also had a new firmware version. The most exciting development there is the introduction of Stripe Scan. So what Stripe Scan allows an operator to do is to physically move the test head forward over the surface and build up 3D data of the concrete under test. So in this case, this test block has conduit for post-tensioning. It has a number of different thicknesses, and we are scanning visually on the left-hand side. So the operator is building up a full set of data, and we're able to cut down in a C-scan view. So we begin at the top of the block element, and as we bring 5 centimeters of thickness through, we first capture a small surface running through the slab. After the surface, we're going to be able to see the larger conduit cutting through. And after that, we'll be able to bring our scan further down and capture the thinner section of the slab through to the thicker section of the slab. Now, this isn't the end of this data. This is simply one way to review it. It's also possible to produce a full 3D visualization, capturing our larger conduit, thinner and thicker sections in a visual presentation. So this is hallmark with ProSec. They're constantly improving the software, supporting their new instruments in the live system. Now, we also have a few conferences left this year. At the start of next week, myself and Warren will be attending corrosion prevention, and we will have a booth there. This is a great chance to see some of the new products in our industrial NDT range and to catch up and talk how we can help in corrosion assessment and durability. Secondly, at the second half of the week in Sydney, myself and Stuart, our GPR expert, will be at the NCEC convention in the Sydney Showgrounds. We're also going to be able to present between 11 and 11:30 on Thursday. In the tech zone will be our presentation on emerging technology, which is developments in ground penetrating radar. So with that little bit of housekeeping done, I'll begin today's main presentation. So the topic for today is testing instrumentation for fresh concrete. So what do we mean by fresh concrete? Well, we're talking concrete that is either newly cast or newly constructed. So I'm going to be covering compressive strength, what that means, how it's tested, and also why it's more of an agreement between parties than it is a direct measurement of material property. Extending on from some of the technology we talk about during strength testing, I'll be able to talk a bit about temperature monitoring of concrete structures. This is also a good chance to talk about some of the new developments we have with our IntelliRock product range. And then I'll finish up talking about temperatures and instrumentation by talking about hot box testing. We'll also talk a bit about cracking in concrete, because one of the main reasons you monitor temperature is to determine that conditions haven't occurred that may cause cracking. But once there is cracked concrete, it's important to understand what can be measured and recorded, and the tools available to do that. So again, fresh concrete, so freshly cast, freshly cured or freshly constructed. So the tools I'll be discussing today are primarily going to be of use during the construction phase of a contract. They're not going to be as relevant to remedial works or repair works, or tools you would bring out to look at an unknown structure. So cylinder testing of concrete is the standard way in Australia to measure and relate a compressive strength between different concrete mixes. Now, the local standard is AS 1012, and specifically there's subsection AS 1012.8 and subsection AS 1012.9 cover the creation of samples of concrete for compressive strength testing. And when I say that's an agreement, what I really mean is it defines a very precise and clear procedure whereby a sample of fresh concrete can be taken, cast as a cylinder, cured in consistent conditions, and broken at a defined moment in time. And by controlling all these factors through the history of that cylinder, that compressive strength, the MPa value taken at 28 days, can then be compared between other similar tests. So if the test mix was cast using certain materials and came out at a 50 MPa strength at 28 days, and then the cylinders taken on site are cast similarly and broken similarly, they should perform the same. And this is one of the tools used to confirm that the concrete being delivered out on site is consistent and correct for the applications. Now, it's only as good a test method as the control over those cylinders. If you have cylinders exposed to fluctuations in temperature, if they're allowed to lose moisture during their life, this has the immediate effect of removing the use of that cylinder as a comparison between the concrete on site today and the concrete on site tomorrow and the whole history of that concrete mix. Similarly, a concrete cylinder taken and cured at 23 degrees centigrade reliably doesn't actually match up with what the concrete on site is doing, So the in situ strength is a little bit of a different thing. I'm going to talk a bit more about that today, but I'm also going to take the chance to point you back to our earlier webinar on early age strength, available on the same channel you're on today. So do subscribe and do review some of the background of what we've done. And we have other tools to capture the performance of concrete strength on site, whether that's making a cylinder break better match on site strengths, or using relationships between temperature and time on site back to strength. Similarly, while the compressive strength test is not a direct measure of a material property of the concrete, like, say, the resistivity, which is a direct measure of bulk resistance, it's still, the units that it's presented in are measured as part of the test. We physically break the sample and measure pressure. Some other techniques that capture an MPa value are correlated measurements. So it's also important when you're thinking about compressive strength to know whether you're taking a direct or indirect measurement of that strength, and if it is an indirect measurement, what correlations are needed to capture that. So, continuing to talk a little bit about the Australian standards, AS 1012.8, this defines the method for preparing a compression or indirect tensile test specimen. There's also another section of AS 1012 which defines how to take the sample of concrete that's going to be cast into the test specimen. And 1012.9 defines how to break that specimen and capture a strength. So the geometry and the basic details of that specimen are 1012.8, and then the actual details of the test is 1012.9. So I'm just going to step through a quick summary of the details to perform a compressive strength test correctly. The casting of the sample is the first stage, and it's commonly used as a 1:2 ratio cylindrical sample of 100 or 150 millimeter diameter. The size used is mainly chosen based upon the aggregate in use and the strength required. It's more common to crush a 100 diameter specimen, but there's conditions whereupon a 150 diameter specimen would need to be used. The concrete 1012.8 also defines very specifically how that sample should be compacted, how many layers need to be placed into the mold, how many strokes of a rod, or how long an internal or external vibrator is used, and also under what conditions those specific compaction methods can be used. The molds also need to be provided with a cover to try and reduce loss of moisture from those samples. Now, curing is the absolutely critical one because it's the curing conditions and the time at those curing conditions that's going to control the strength that's achieved. So the conditions are defined by where in Australia the sample is being prepared. So in New South Wales and beneath, it's a 23 degrees temperature. And then in the tropical zones, it's a 27 degrees temperature. It also defines how those samples are to be stored before they're broken. And it's that storage period that can have a big effect, because if you take those cylinders in a very hot day, and they're going to get well above the 23 degrees standard curing temperature. So they should be in a climate-controlled environment, protected from the sun and protected from moisture loss. We actually do have an easy cure product, which we saw a couple of slides before, which is a air curing box intended to maintain that 23 degrees temperature and provide a protected environment for molds to cure in during the initial curing. These then need to be transported and placed into wet curing, either immersed in a temperature-controlled water bath, or occasionally in a fog room where required. The Queensland, now, I'm talking about the Australian standards. It is also local specifications, which we'll talk a little bit more about specifications shortly. But they're going to be an additional tool that may define how cylinders need to be prepared. So whenever you are working with concrete strength, there may be additional conditions beyond those in the Australian standards, or it may be that you're working to an international standard or a different test method for that project. Now, the break of the sample happens at 28 days for a standard compressive strength test. It may be a little bit different if the break was taken at another time, either a later strength test to allow for additional hydration of the concrete, or an early age strength, which I'll talk about in a moment. And as part of that procedure, the specimen should be inspected. Anything which is not cast should not be used for the testing, and any unusual things should be documented. Now, with a cylinder mould, there are smooth surfaces around the circumference and on one base of the concrete sample, but the top surface is rough. So that needs to be capped or ground to complete the test correctly and allow it to sit plain and not have an effect on the final test. Now, cylinder grinding is a very common way to achieve that, where the cylinder is ground plain and flat to 0.05 of a mil. And the main purpose of that is simply to allow the pressure to be consistent over that entire surface. Grinding has some advantages over sulfur capping or rubber caps. It's more generally applicable to a greater range of strengths, both high and low, whereas rubber capping is limited in the strengths it can be used for. It's also more consistent because the grinders will ensure an even, clean finish of the same strength as the material under test, which can be seen as less scatter in results, a more consistent break between samples of the same concrete, which makes which overall improves the statistic properties of that test under mix. And finally, it also defines the load rate of the test and how that should be reported. So forces applied, compressive strengths, types of caps, anything obviously different to the standard and the standard it was tested to. Now, we've talked about 28-day cylinder strength. That's a very important way to document the performance of the concrete. But it's not the only compressive strength that matters to people in the field. But sometimes it's more important to know the in-place strength of the concrete, particularly where there are criteria to allow work to continue, whether that be the removal of formwork, the application of post-tensioning, or the turnover of a precast mould. So that's where early age strength measurements come in to check. As I said, we do have a previous webinar that goes into a lot of detail on this topic and compares between early age cylinders and then attempts to match the temperature of cylinders under test to the in situ concrete to better capture the real strengths. It also captures a number of correlated methods, such as Schmidt-Hammer tests or maturity tests, which try and capture the strength in site in a non-destructive manner, whether with an embedded temperature sensor or with a tool like a Schmidt-Hammer. When you're working with these tools, it's important to understand what the temperature is being captured for and what's going to be most appropriate, and also how critical that value is. Now, since the previous webinar was presented, we are very happy to have a new version of the IntelliRock maturity range, which is the IntelliRock 3. And for this product range, the biggest improvement is this is now a genuine internet-connected system. There is, once the temperature loggers are placed out on site and connected into a wireless box, the data is immediately available by any web browser to the operator. And that's not just a temperature history or even a maturity calculation. The web app now prepares the early age strength according to the defined maturity calibration and can send out notifications of achieved strengths or other limits that might be important to the site, which I'll get to in a second when I talk about bulk temperatures. There's also been a changeover for the IntelliRock 3 loggers. These are now a logger that works for 180 days rather than, say, a 28-day temperature every 15 minutes, and they're recording data every 1 minute for the maturity calibration. And for temperature monitoring, the setup is actually done by the user now, but generally 5 minutes to 1 minute, depending upon how they're set up inside the web app. This is a big improvement. There's no need to set up, to visit out on site and connect data with any particular tool. Once they're hooked in and running, you have immediate access wherever you are on the site to the strengths or the bulk temperature logging. The other advantage is that it's still the IntelliRock logger system, so it's still the most secure concrete strengths available. The data on an IntelliRock logger, is stored safe and battery protected in the logger itself. And whether you have a reader or a wireless box connected, that information is never lost, it's never overwritten. It's stored securely for the history of the project. And once the logger finishes its 180-day run, that temperature is still available for as long as the internal battery remains, generally 6 months or so. So there's never a chance where an important specified monitoring point is not captured. And even if there's an issue with cable damage or batteries for wireless communication, you can always re-terminate and collect the data. Your results are secure. And you can immediately see that on the web app and fix the problem right away. So, continuing on to bulk temperature. Bulk temperature monitoring is becoming more and more important in Australia, and the specifications are changing a bit. Whereas it may have been more common to have a maximum 80-degree temperature limit and a fairly loose differential temperature, the specifications have now tightened. 5100.5, released in 2017, now defines a maximum temperature of 75 degrees centigrade and a differential temperature of no more than 20 degrees, in each case defining that the maximum temperature take into account lead etching formation and the differential temperature to control for thermal cracking. Now, they do define monitoring, but it's not the monitoring that's going to prevent the strength issues, to cause the cracking issues or the performance issues. It's the curing environment and the care taken during the pour that are going to control for these. Things like insulated formwork, delivery of cold water with concrete, and the use of the correct mixes for the application is what's going to meet these criteria. But it's the temperature monitoring tools that are going to give the input to the designers for the mixes and for the on-site construction that's going to allow those decisions to be made. Now, I've pulled a few more points of interest here from around Australia, in that Queensland Transport and Main Roads has its own specifications, which are a little bit looser than 5100.5. And the RMS B80 is tighter on a absolute maximum temperature, but has no defined differential. It comes to a different reference. Though Transport New South Wales has its own criteria as well. Critically, it's not going to be just, it's going to be the specification on the project that's going to control what needs to be met. Now, the final thing I want to talk a bit about today is cracking of fresh concrete. So, it's been monitored to ensure it performs the way it should, and that's part of the specification. But the other part of the specification may be that cracks above a certain dimension need to be recorded and in some cases rectified. So that could include crack mapping, so mapping out where on the structure the cracks are found, dimensions of the crack, such as the width or the depth of the crack. And whenever you're recording physical measurement, it's really important to record what's happening around that as part of a test. So if it was a crack width measurement, it's important to know where on the structure that crack was, what conditions that cracking occurred during. Was the day unusually hot or unusually cold, or was there some other factor that might affect it? And also the conditions of the concrete. Now, having reviewed standards and specifications here, the standards typically talk more about how crack performance is to be achieved, but specifications define the requirements for cracking. Now, so VicRoad 610 has a maximum crack size of 0.2 of a millimetre to 0.1 of a millimetre based upon exposure. The RMS B80 has a requirement for cracks during curing and a second requirement for cracks at 28 days. And it requires that if they do occur, they be mapped in place and recorded. Transport for New South Wales doesn't have a particular reference, but does have a maximum aesthetic standard, which only applies where corrosion is not an issue, because the main reason to control for cracks is the long-term durability of the structure. Furthermore, the standard Z706, sorry, not standards, the Concrete Institute of Australia guidelines, Z706 and Z715, talk more about the causes of cracking, performance of concrete in general, and how to work intelligently with these issues. The Z7 series is an excellent reference for working with concrete. And finally, AS3600 has more, uses crack width more as a design input, and also, and then talks about how the structures can be designed to meet the crack sizes. Now, crack depths can be recorded using pulse velocity tools. This is a trigonometric way of measurement, so it's based purely upon an assumed triangular path of sound through concrete. By recording transmission times between points over a crack, it can be mathematically determined, with input of the velocity, the depth of that crack. Now, normally it's very hard to capture depths of cracks without feeler gauges for large cracks. So this is one possible way, when the crack is open and clean, to document a crack depth. Crack widths are normally monitored visually, and we're very pleased to now have a computer-based little handheld computer crack width camera, which will measure and record the width of the cracks visually. So this greatly speeds up the measurement procedure. And it's very precise. It's able to measure cracks as fine as 0.02 of a millimetre. And it's also captures things the right way. So in this case, we can see on the left-hand side, we've captured the internal crack width, not the damage that's occurred at the edges of the crack where it's spooled away slightly. Finally, another important tool when you're considering concrete's performance and temperature is to actually understand how that concrete cures. Now, ideally that would be what's called an adiabatic test, where a sample of concrete is allowed to cure in an environment that neither removes or adds moisture to that curing. So essentially it's capturing the real heat of hydration of that concrete. That's quite a complex test, and it's normally done in a laboratory. But the Concrete Institute of Australia's Z707 document does talk about a test that can be used as input for modelling. That's a little bit easier to achieve. It can be done out in site or at batch plants. And that's where a 1 metre concrete cube is prepared in a hot box, which is a insulated plywood box, 1 metre by 1 metre. The strain and the temperature at various points in that box is monitored, and this provides direct input for the real curing heat of that concrete. We've done a lot of work with some of our data logging options to produce prepared packages which have everything you need to complete a hotbox test in terms of monitoring. So that's temperature sensors, that's strain gauges where required, and that's the data logger, all in something that can be set up and worked with by technicians or engineers from your concrete company or on site. There's no data logger programming to be done, and it's a very useful way to conduct this test, which is very straightforward. And that can. This is actually something we always have available as well. There's always units like this available on the shelf, and we always have our strain and temperature sensors available. So that's just a quick overview of some of the tools and some of the considerations for testing a fresh concrete. It's not exhaustive by any means, but I did want to ask now if anyone has any questions or other input I can provide while I'm here. And for those of you who are going to stay on, thank you so much for joining us. And I always appreciate the chance to talk a little more about some of the background in our industry and also the specific products and tools that PCTE has available. But I'm watching now, so if there's any questions, please just ask them on the right-hand side in our chat box. Sorry about the phone. I have control over my mobile, but not the office phone. Okay, so give me a second. I'll pass on a few links. So that's our maturity logger system and the temperature logging system from IntelliRock. This is the new crack measurement camera. Now, I'm going to, for the sensors, now these are assembled, the hotbox system is assembled from our structural sensors range. So I'm going to share a link to that for the hotbox relationship. Was that all, Peter, or is there something else I can pop up for you? Oh, and of course we had the products mentioned at the beginning, so the ProSec GPR for and for resistivity, that's under our corrosion in concrete range. Where we have the ResiPod from ProSec. Now, about resistivity for durability, probably best I talk with you personally. I'll reach out shortly. Now, actually, while I've got a chance, I may actually talk a bit about the structure of our webpage. So I'm just going to bring over the webpage onto the screen here and bring that full screen. For those of you who haven't seen our webpage before, there's a lot of information available. So I'm going to go to the home page, and from here, all of our different product ranges, apart from our new industrial NGT range, which exists on a different webpage, is available under the grids. So if I wanted to find my temperature instruments, I could go to Instruments and follow down the chain to find structural sensors or temperature sensors or geotech sensors. And there I can find the products that we were discussing right away. Similarly, if I wanted to learn about GPR, I can use the top links to find the GPR ranges and maybe take a look at the ProSec unit. And we normally have a live chat box available too. It's actually our sales staff monitoring that, so you should get expert advice and support out of those boxes if you do reach out to us. Now, was there anything else I can help anyone with while I'm available? All right, look, I'd like to thank everyone very much for attending our webinar. If there is any more information we can offer that you'd like to talk about personally, I'm always available on the New South Wales phone lines, or you have your local staff members throughout the country. I'm really looking forward to seeing those of you I can at the upcoming conferences, and thank you for your time today.